Okay, so when does the P sequence converge? As long as P is positive. Any positive number, any number greater than 0, that denominator will get big, and it will converge to what number? 0. As long as P is positive, that denominator gets big as I gets large, and so that goes to 0. When does the P series converge? P is greater than 1. When P equals 1, what series is that? That's the harmonic series. We showed that that diverges, right? And so if you make P less than 1, that's going to be even worse than the harmonic, right? The lower you make that exponent, the larger your denominators are. And so if it's less than 1, then that's going to be even bigger than the harmonic series. So that will diverge, okay? If P is greater than 1, so if it's 1.001, that series will converge, okay? Series, when you sum them up. Okay, geometric sequence. What is a geometric sequence? So here's where your index is in the exponent. And what does this sequence end up being? So what's the general idea of the sequence? As you go from one term to the next, you always do what? You multiply by one more r, right? You keep multiplying by more r's as you go, right? So it's like whatever your base is, you go from one to the next. And when did that converge? Converges when? Between 1 and negative 1. Between 1 and negative 1, it converges to 0, right? Because you keep taking some fraction, so you keep multiplying by that same fraction over and over again, it's going to shrink to 0 eventually get very, very small. Yeah, I is our index, right? I is always 1, 2, 3, 4, right? So I is which term we're on, right? So yeah, so R is the thing that changes from one geometric sequence to the next. And so if R is between negative 1 and 1, that thing converges. There's also the trivial one that converges if R equals 1. If R equals 1, it converges to 1, because you just get 1, 1, 1, 1, 1, okay? But that's kind of a trivial case. This is the one we're more interested in. Okay? How can you quickly conclude that a series diverges? What's that? Limit of what? Of the sequence, right? So if you look at the sequence and that limit doesn't go to 0, the limit is not 0 of that sequence, it doesn't go to 0, boom, series diverges, right? That's the divergence test. So then on the flip side of that, what's necessary for a series to converge? What has to be true? The sequence has to go to 0. And does that guarantee that the series will converge? No, okay? And so this is the next week or so of class, or a couple weeks. We'll have a sequence that goes to 0, and we'll be asking the question, does the series converge or not? This is a big theme of what's coming up. Okay? So we're going to look at geometric series today. Geometric series. So we saw a geometric sequence. We said r to the I. So I'm going to change it a little bit, but it's still the same idea. We're going to say a times, so a is any constant. A is any constant. And then rather than do r to the I or r to the j, we're going to do r to the j minus 1. So they've just all moved back 1. Okay? So what I want you to do is, when you see this, what does this mean, right? See this, think what? Write it down. You see this, you think what? Write it down. Alejandro, did you get it? Tell me. Okay. You got it, okay? And what's r to the 0? So that first term just becomes a, right, okay? So when j is 1, you get a. And when j is 2, you get a times r. When a is 3, when j is 3, you get ar squared, and then this tells us to sum those all up. So this is what this means. That's what you should have wrote. So the difference is between what we talked about, the first difference is that every term is just multiplied by a constant. that doesn't faze us much, right? It just allows for a geometric series to have a bigger family, okay? So we can allow for this thing when we add them together to be more. So there's more possibilities by allowing a constant multiplied in front. And then rather than start with r as the first term, we're starting kind of like with 1 as the first term. That's what putting the j minus 1 did. So by having j minus 1, then we get this first term of the geometric series just being the a. If we had done a to the j, well, then the first term would have been ar. But in a geometric series, we allow for that first term to just be the constant a. All right. So this is the big question. For what values of r does the geometric series converge? So for what values of r, if we were to add up all these things together, would we get a finite number? That's what we're saying. We're going to get a finite number. That's the big question. So let's investigate that. And to investigate, let's recall how does the sequence converge? Again, one more time. How does the geometric sequence converge? If what? What's between -1 and 1? R or J or A? R, okay? So when that base R is between -1 and 1, is when we get that sequence to go to 0. And that's actually going to be important when we're working through how the series converges or not. Okay? All right, so here's what we're going to do. We're going to take the sequence of partial sums and look at the kth term of the sequence of partial sums. So the kth term is a plus ar squared all the way out to ar to the what? Not k. Ar to the k minus 1, right? So it's because we're doing ar to the j minus 1, then the kth partial sum is the last thing we add is ar to the k minus 1. Does that make sense? So there's our kth partial sum. And what we're going to do is we're going to take that same thing again and multiply it by r. So take kth partial sum and multiply it by r. And you say, why do you do that? You say, because it works. Okay? Because it works. So this is something that works to help us find what the sum of the series is. So I multiplied that top row by r, and then I moved it over to line them up. Do you see how they line up now? So r times sk would mean r times a plus ar squared plus ar cubed, and the last one would be ar to the k. So then I just shifted it over so that the like terms line up. Is it okay? And then what we're going to do now is we're going to subtract. I'm going to take s sub k minus r sub k, and you see all those middle terms go away. And what's left is all we have left from the first partial sum is a, and all we have left from the second partial sum is ar to the k. So when we subtract, we get a minus ar to the k. Do you see it? All these go away. Ar minus ar goes away. Ar squared minus ar squared goes away, etc. So all these middle terms, when I subtract, they just all subtract to 0. And I'm left with a minus ar to the k. Yeah, this would be k minus 1 right here. Yep. Sorry, was that confusing? That should be in k minus 1. Is it okay? Yeah. So what does r to the k minus 1 mean? What does r to the k minus 1 mean? Yeah, but what does it mean? Like our quiz, what does it mean? R to the k minus 1 means? Do what? Multiply r together k minus 1 times. So now if I multiply it by one more r, so I'm going to take r to the k minus 1, or r multiplied together k minus 1 times, and multiply it by one more r. Now how many r's do I have? multiplied together. K, I have k r's. So that one, when I multiplied by r, that one became this. This was the last term, and so when I multiplied it by r, now it's k r's multiplied together. Yeah, so this term was this one, but then after I multiplied all of them by r, then I shifted them all over. Just physically, I just moved them, right? Okay, going on. So I can factor out my partial sum, and that's s of k times 1 minus r, and I can divide, then I divide by 1 minus r. And then I take the 1 minus r as a common denominator and make a subtraction of two fractions. So this is just algebra. I was just doing some algebra here. And then how does the sequence of partial sums relate to the series, the sum of the series? How does the sequence of partial sums relate to the sum of the series? Yeah, if you take the limit of that sequence of partial sums, where is that sequence heading? It's heading to the actual sum of them all, right? Because if you keep adding one more term, and you just keep doing that, then that sequence of adding one more term is getting closer and closer to the whole sum, right? So that's what we're going to do. I've got a general form. I'm going to take the limit of this. If I take the limit of this, it's going to be the same as the sum, right? We've seen that before. So the sum of the series is the limit of the sequence of partial sums. So I'm going to let k, I'm going to take the limit as k goes to infinity of that formula that we found for the sequence of partial sums. So there's two things going on here. First of all, we need that thing to converge to a finite value. And so then we're asking what values of r will make that converge. That's the first thing we need to do. So, okay. All right, so I've got this thing we're working on right here. A over 1 minus r does not care what k does. K can do anything it wants. It's just a over 1 minus r. So this does not pose any problem. Okay? But as k gets large, we need this thing to behave. Okay? We need this to behave. So look what we have. We have r to the k. What is that? That's just the geometric sequence, right? R to the k. When does r to the k converge? When r is between -1 and 1. If r is not between -1 and 1, this thing blows up, right? This thing will get really big. So if r stays between -1 and 1, according to our geometric sequence, then this fraction will do what? Converge to 0. And when this converges to 0, this limit is a over 1 minus r. So what happens? If we have a convergent geometric sequence, if r is between -1 and 1, this goes away as k gets large, and we're left with a over 1 minus r, which is the limit, which is the sum of the series. So that limit is the first term, a over 1 minus r, if r is between -1 and 1, because that makes this sequence here converge to 0. So not only did we find out when the geometric series converged, but we find out what it converges to. We can actually calculate the sum very easily. So it converges when r is between -1 and 1, and then the sum is a over 1 minus r. So we wanted to know when it converged, but we got this bonus of Hey, look, now given a geometric series, if it converges, we got an easy calculation to figure out what it will sum up to in the end. All right, any questions on that? Yeah?
If R is larger than 1 or less than -1, it would all diverge.
Yeah, well, so then you have a then you have a divergent sequence of the. We wouldn't even need all this because if R is outside -1 to 1, then that sequence diverges, and then it's like a divergence test. Yeah, yeah.
I'm still kind of confused how you turned like the minus R S of K into 1 minus R.
This one here,
There,
I
yeah.
just factored out S sub K. So this is S of K minus R times S of K. If you factor out S of K, it leaves 1 minus R. Yes, sir.
So the last equation, if R is -1, doesn't that give you 1 minus -1, which gives you a factor over 2? Means
No.
K over 1 minus R.
If R is -1,
Yeah.
then this thing keeps jumping back and forth. This thing doesn't. If R is -1, that does not converge to 0. It keeps jumping back and forth. So if you don't have a sequence that converges to 0, you can't have a series that converges. Remember that? Yep.
S of K is supposed to be the partial sum. Why is it the second term A plus A, A plus A plus AR? So it's like A plus.
Here's looking right here.
Yeah. Why is it A plus AR plus AR squared? If it's supposed to be a partial sum, shouldn't it be A plus AR plus A plus AR plus
No, you're doing a sum of the sequence of partial sums, and that's not something we do. So you're taking the sequence of partial sums and you're making that into a series. Yeah.
If R equals -1 or 1, it will still diverge.
Yeah.
Does it have to be in between? It has to be in between.
Yes, it has to be in between. So there's that trivial case where if R equals 1, the sequence converges to 1. But if the sequence converges to 1, we still know the series doesn't converge because it's not converging to 0.
Yeah.
So this is all we care about because it's when the sequence converges to 0. And it turns out if the sequence converges to 0, the geometric series also converges to A over 1 minus R. That's what we found out. That's the same requirement for the sequence to converge as it is the series to converge. It ends up being the same requirement for both. Okay, so let's look at an example. So the turtle is still, since we started, the turtle is still making its way across the backyard. Remember, he walked half the yard the first day, and then a quarter of the yard on the second day, and then an eighth of the yard on the third day. And so that's a series, right? That's the series. Let's write that out. What series is that? 1/2 plus 1/4 plus 1/8. Can you write that expression? Can you write that in a concise way that a calculus student would understand? All right, so write that in a more concise way that a calculus student would understand. Should be able to. Would that be Caden? Did you get it? Tell me. One over 2 to the I. I use J. So it's summation of 1 over 2 to the J as J goes from 1 to infinity. That's what you should have wrote. Or you could have used I if you wanted I or K. Doesn't matter. Okay, so notice what kind of I could also write that as 1/2 to the J. What kind of series is that? This is a geometric series, okay? This is a geometric series. And if we want to, so will it converge, first of all? Will it converge? Why? Because our R value 1/2 is between -1 and 1. So this will converge, okay? And next question is, is it in the form that we need it to be to use our a over 1 minus r formula? Is it in that form? No. What's wrong with it? Our exponent needs to be j. We're starting at the right number. We're starting at j equals 1. That's fine. We need 1/2 to the j minus 1. So here's where your knowledge of exponents comes in. I need my sequence to be 1/2 to the j. But I need to have 1/2 to the j minus 1. So how do I adjust this? So I've preserved my sequence being 1/2 to the j. So it goes back to the meaning of exponents. This means j number of 1/2s multiplied together. This means how many 1/2s is this compared to that many? One less. So if I want to preserve, I want to get j, what do I need? I need one more 1/2 multiplied out here in front. Do you see it? Now I still have, I've just rewritten it in a different way, but I still have j number of 1/2s multiplied together. Do you see it? Okay, now does it fit the form? And since we have a convergent geometric series, it's equal to a over 1 minus r. A is 1/2, right? Over 1 minus 1/2. This 1/2. So we proved on the previous slide that if you have a convergent geometric series, that it will sum up to all infinitely many terms summed together will sum up to a over 1 minus r. So we get 1/2 over 1/2 over 1/2, which equals. So the sum of this series is the number 1. And we ask the question. He walks 1/2 the first day, a quarter of the lawn the second, an eighth of the lawn the third day, a 16th of the lawn, etc. He keeps doing this. Will he ever make it across the back lawn? Yes or no? Yes, if what? He's got to keep, he never stops. He never stops. If he ever stops and we look at a partial sum, then he will not have made it. If you ever look at a partial sum, even if it's the trillionth partial sum, precisely he doesn't make it. But if you add together all the terms of this series, which means all infinitely many terms, he makes it. He makes it across, he makes it to the other side. Meaning this total distance, right, that's his total distance walked, is 1 yard length, right? That's his total distance walked. Half the first day, quarter, an eighth, 16th. So then, if you count all the days in the series, you will walk 1 full yard length. But if you take any partial sum, he doesn't quite make it, right? So you can't think in terms of partial sums. You've got to think in terms of the sum, or the limit of partial sums. All right, questions on that? We'll check on his progress at the final exam. All right, another example. Here we go. So this one's more complicated, and what's the goal? The goal is to get it to look like a times r to the j minus 1. We got to get this thing to look like, so that this takes more using our knowledge of exponents. So I'm using eyes now. So I'm using eyes now on this one. That's fine. So how do we rewrite this expression so that it ends up in the form a times r to the I minus 1? Then once we have that, then we can analyze it more easily. Okay, so what's our r value going to be? First, we got to figure out what r is. A is going to take some time to get. What is r? Do you see that r should be negative 3 over 4? Okay, because I got negative 3 to the I plus 2 and 4 to the I minus 2. So we keep multiplying by a negative 3 on the top and a 4 on the bottom as we go. So this is, we can group those together, negative 3/4. So then how many negative 3's do we have? I plus 2, and we need I minus 1. So we need this whole thing to have a number of negative 3's to be I plus 2 on the top. Right now I have I minus 1. So what does that mean? How many more negative 3's do I need on the top? Do you see I'm going to need 3 more? If I've got three negative 3's and I minus 1 negative 3's, then I'll have I plus 2 negative 3's. Do you see it? All right, now it's a little more tricky. So now I have I minus 1 4's. What I really need is what? I minus 2 4's. So this is what? This is too many 4's. How many too many is it? This is 1 too many 4's in the denominator. So how do I get rid of a 4? Yeah, or we could do a 1/4 down here. So if I do a 1/4 in the denominator, that's going to take away one of the 4's in the I minus 1 4's, and then I'll have I minus 2 4's. And we still have the 5 down here. All right, did I lose you? Yeah. No, the A is all of this. It's everything multiplied by the R to the I minus 1. So what is A then? 4, so the 4 can come up top. So 4 times negative 27 over 5. So this thing equals A, which is 4 times negative 27 over 5. There's our A. Over 1 minus, what's R? And I'm only doing this because what? Why can I do this? Because our negative 3/4 falls in the range. It falls in that range for convergent series. So whatever this number all turns out to be, it's going to be the sum of that series, which converges because R is between negative 1 and 1. Caden? Because every time I go to the next term, I keep multiplying by another 4 in the denominator and number 3 in the numerator, right? So, because I keep increasing I by 1, so I'm just going to gather them together, but work out what I need here. Yeah? How did I get what? There is no negative here. This is A over 1 minus R. This is, remember, when it converges, the whole thing equals A minus 1 over R. So I'm just using that formula. Okay. Any questions on that example? So whatever that turns out to be is the sum of that series. Okay, there's something called the comparison test. We actually used this when we did harmonic series. This is exactly what we used to show that the harmonic series diverged. Okay? So if you have two series with positive terms, we're asking about this one. Okay, so we have a series AI. If there's another series, say BI, and it's divergent, and the one we're analyzing, every one of its terms is greater than the terms of the one we know is divergent, then the one we're analyzing is divergent. So this was like the harmonic series. here are our terms in the harmonic series. 1, 1/2, 1/3, 1/4. And what do? We said we'll compare it to 1, 1/2. 1/4 plus 1/4. And then 1/8 plus 1/8 plus 1/8 plus 1/8. And we had this other series, and we knew that it diverged, but the one we were looking at, the harmonic series, its terms were greater, right? Its terms were greater than or equal to all the terms of this other one, and so then we conclude divergence. So basically, if the one you're looking at is bigger than a divergent series, then it's divergent. That's the thing. But we have to look at it term by term. We have to say every term of ours is bigger than or equal to the term of this other one that we know is divergent. Then we can conclude ours is divergent. So then what would a comparison test for convergent series be? So we've got one. We think it might be convergent. What would we need? We need to compare it to convergent series. And how does that convergent series have to compare to ours? All the terms would have to be larger, right? So if there's a known convergent series and all of its terms are larger than the one we're working on, then ours would converge too, right? So here's that. Let's just do one. So 1 over I cubed plus I plus 2. Do you suspect that that converges or diverges? Because? So this is very much like what kind of series? A p-series. And how do all these terms compare to the p-series of 1 over I cubed? All these terms are, for every I, this is always smaller than that. And we know if you sum all these up, it converges because this is a p-series, p greater than 1. So if all these terms are smaller because you're having a bigger denominator, then that must converge as well. So that's the idea of the comparison test. So then if every individual term sums up to be less, then the whole sum is less. And if this is convergent, then that must be convergent as well.